Hi, I'm David Kohlbrenner. This is work with Mark Andrisco, Keaton Mowry, Ranjit Jala, Soren Lerner, and Hoval Shakam, my advisor, all at UC San Diego. And we're going to be talking about floating point and side channels, so not caches. So that's cache. We've been talking a lot about caches. You've seen a lot of cache attacks. But we're going to talk about a slightly different part of your processor today, a little bit less understood, the floating point unit of your processor. So let's run code on our floating point unit. We have two programs here. Both of them perform the same multiplication 100 million times, except one of them multiplies 1.0 times 1.0, and one of them multiplies 1.0 times a rather suspiciously small value. And if we just run these two programs in user land on Linux, and we time them using Unix time, we see that one of them runs in 0.2 seconds, the other one runs in 4.3 seconds, which is over 20 times slower. So that's a little bit disturbing. Who knew that if I wrote these two programs, they would run 20 times slower? Well, numerical analysts knew this, and CPU designers obviously had to build this. Game engine authors have great blogs detailing how to avoid this behavior. But I would argue that a lot of us didn't know it, and we probably should have, because we all read what every computer scientist should know about floating point arithmetic, which was written in 1991. And as a kind of an example here, one of the systems that we examined and we were able to find a floating point side channel in, the authors stated that they, quote, claimed to effectively close all known remotely exploitable channels, specifically referring to timing side channels. And we have a functional timing side channel attack against their system. So let's learn a little bit about floating point and timing, because obviously they run rather strangely. Well, what just happened in the code I showed you? Well, there's this IEEE standard, which was standardized in the late 80s. There's these subnormal floating point values. Let's actually look at them for a second here. So there's these subnormal values, but first we're going to talk about normal values. This is an IEEE 754 64-bit double. You have 52 bits of significand, you have an exponent, you have a sign bit, and this value that it represents is here. One thing to note is there's a bias value applied to the exponent, and this lets you represent values a lot easier. And a normal value, the exponent, those 11 bits, are non-all zero. So you set something there. And this specifies then that you have an implicit leading 1 bit on your significand. Now, the IEEE standard also specifies a subnormal floating point number. And these are an optional part of the standard, but most CPUs implement them. And in the subnormal case, your exponent is all 0 bits, and you have an implicit leading 0 bit on your significand. Now, if you're doing the math, you're going to say that is an incredibly small number, and yes, it's an incredibly small number. This is your range, and I've included the Planck length there for scale. Now, why would you want numbers that are so incredibly tiny? And these are just doubles. Well, one thing is it greatly extends the representable range of floating point values. You've got a much larger range of representable values. And kind of getting back to our Goldberg, we have a graceful underflow problem here. If I were to perform this check and math with integer arithmetic, you would agree with me that a minus b is never going to be 0, and we would never divide by 0. But with floating point, this is not true, because we can end up with a situation where we have values that are too close to each other. With subnormal values enabled, you are guaranteed that no matter what a and b are, you will never result with 0 in this case. So there's a kind of a safety and correctness property that's nice to have here. So what happened? Let's get back to that. So we have these subnormal values. I just kind of explained to you, though, that they're not the common case. And the FPU that you have, the floating point unit, is designed purely for speed. That's your goal. So most of the time, they're just going to kind of pretend that they don't matter. And they end up being a hardware slow path on all processors today that are your commodity processors. Notably, for example, as kind of a motivation here, the alpha trapped to kernel every single time it got a subnormal as the result of a computation. And that's a machine that wanted to be quick. And also, most GPUs don't support these values. Some newer ones, there's some differences. But the majority of them will simply treat them as 0 if they encounter them. Now, I'd like to argue that floating point is a security issue for several reasons. But this is not the first time that floating point has been misunderstood. There's a fantastic piece of work by Ilya Mironov on Laplacian noise generation. there was a system that was attempting to generate uniform random noise. And rather than end up with a beautiful probability curve that like you would expect, they used a naive way of generating this noise, and they got this Bowser's castle of probability distributions, which I don't need to explain to you before you'll know that that's probably not what you expected. And there's also kind of this issue of dependable results. When you use floating point arithmetic, recompiling your program can result in not only different running times, but different values out of your computations. And this is especially noticeable if you start doing things like changing your optimization flags. So if they run in different amounts of time, how do we leverage this into an attack? We're going to need to get to timing attacks, and I haven't even talked about them yet. So on a timing attack, you want something that operates on secret data and attacker data, and you want it to have some sort of difference. So we've seen instruction traces, we see memory access patterns, cache utilization, IO utilization, et cetera. This work presents the first practical instruction data-based timing side channel. So our attacks have identical code paths, identical memory access, identical IO access. The only difference is the value that's represented in our floating point registers. And this was proposed by Kocher 20 years ago in the original work on floating point, but there hasn't been anything since. So this is some kind of random data from our paper on floating point. On the top we have a Core i7 processor, and on the bottom we have an Atom Intel processor. And the blue is SSE instructions. These implement your IEEE 754 standard. And on the other side we have our orange, which is the x87 unit. Now you might not have been aware of this, but your processor actually has two entirely independent, non-compatible, and non-conforming floating point stacks. And your compiler is deciding which of these to use, and you're going to get different results from them. So we have add and division for SSE, and we have add and multiply for x87 here. And these are all normalized graphs to how long add normal value plus normal value takes. So on the i7, as you can see, we have some variation. Division where the normal and subnormal is nasty. The x87 is worse on both of these, and the Atom is notably kind of all over the place. So these are just for normal and subnormal, but there's actually a wide variety of timing differences with special cases like zeros and ones and extra large values and that sort of thing. And you can see the paper for details on that. So these, as I said though, are cycle count differences. So when I say that, oh, this one's like twice as long, I'm talking about 7 cycles versus 14 CPU cycles, which on a loaded system is going to be a little bit difficult to spot. And if we go back to that code I showed you at the very beginning, we're going to need a way to amplify this timing difference. And I did that in the sample code. I just ran the math 100 million times. So we want code, if we're going to use this as a side channel, as a timing side channel, we want code that runs tight math loops over repetitive data so that we can amplify our attack. Which means we need to now take a detour. I've been down in the low level talking to you about FPUs. I now need to talk to you about something that we can attack. Specifically, I'm going to talk to you about Firefox. And to do that, I'm going to talk about Firefox SVG filters and summarize a previous attack that used Firefox SVG filters, because ours looks pretty similar. So what's a Firefox SVG filter? Well, a Firefox SVG filter is a CSS thing that lets you turn this, a iframed copy of Wikipedia, into this, which is a blurred iframed copy of Wikipedia. This is very valuable, as we all know. It does actually let you do other things than that. You can apply it really to pretty much any DOM element that you would like, notably iframes in this case. And you can run over a variety of different functions. You can run your blurs, your skews, gradients, clipping, et cetera. And very importantly, these are stackable filters. So I can apply 10 of these filters in a row composed and get back out a different result. So I'm going to go over now kind of a high-level version of Paul Stone's pixel-perfect timing attacks with HTML5. This was an attack on Firefox privacy that used SVG filters. The purpose of it was that an attacker web page could iframe a victim web page and then read pixel data out of that web page, effectively violating the same origin policy. So that's what we have right here. We have an attacker web page that is iframing a target web page. We're going to pick out some pixel. We're just going to highlight it as red. Let's pretend pixels are black and white for now. And we're going to expand this pixel. And we're going to do this with some filters. We're going to use some divs, a couple of kind of silly CSS elements. And you're going to end up with a div that contains that target pixel as many times as you would like. And then in the Paul Stone case, we're going to run an SVG filter over this. We're going to run, he runs the FE morphology filter over this, and you obtain a filtered rendering of that div, which you immediately throw away because you don't care about it. But you time the rendering of that. And you can use JavaScript to do this. You can use JavaScript, you can set callbacks for animation frame timing, and you can get high performance timing counters out. And you time this, and in the FE morphology case, there was a fast path in the code for the filter. If it found an image that looked very similar across all of itself, the code ran quicker than in other cases. And this is actually an excerpt from that specific code. So there was this fast path optimization. And by utilizing this fast path optimization, the attacker was able to read out pixel data. Now the fix for this was to write constant time code, which is something that should scare everyone. And it took around 2 years to land the patch for this for various reasons. There's an enormous bug thread. I highly recommend reading it. It's very interesting. A lot to say about Mozilla. And kind of it boiled down to them trying to implement a couple key parts as constant time things in C++. Okay, so I'm going to now shift us back to the present. Let's remember that we have our subnormal floating point. We have this SVG attack. And really, Firefox SVG filters weren't fixed, right? The filters were just written to be constant time, but we still get to compute over foreign pixel data. And I have a brand new timing side channel source for you. But I told you that, well, and I guess it should be no surprise at this point, but SVG filters run floating point math. So this looks really good for us. But I still need, why did that not go? I still need an amplifier, remember? Because I ran my code 100 million times. Thankfully, 10 seconds ago, I showed you an amplifier, which is that I take a target pixel, and I'm able to expand it to be as many pixels as I want, and then run a filter over it. So that's exactly what I'm looking for. Now, this is a simplified version of the convolution filter in Firefox, which is what we use to implement our attack. So this is run over every pixel in the target div that you're running it over, and it's going to take a swatch of nearby pixels, and it's going to multiply it against a kernel. The kernel is what is controlled by the attacker, and then it's going to sum up the result of that multiplication and set that to the new pixel value. So the sorts patch in this case is the unknown data of some sort, and we as the attacker have set the kernel to be some suspiciously small floating point values. And so there's going to be two kinds of sets of math that occur. The first is this multiplication. And let's pretend that our pixel datas are just 1 or 0 for this case. You're either going to be multiplying 1 times the subnormal value a bunch of times, or you're going to be multiplying 0 times the subnormal a bunch of times. Now this does actually turn out to have a timing difference, but we don't care about it very much. What we care about is that this fills temp up with either subnormal values or zeros. Because then at the bottom we're going to sum everything up, and summing subnormal plus subnormal versus 0 plus 0 is an enormous timing side channel. And we do this as many times as we want because we simply expand our pixel as big as we need, in our case 200 by 200 pixels. And we're able to time the running of this, and we get out about a 20 millisecond on most machines difference. And that's measured from JavaScript with a browser running and all of the usual Gmail open. So this is, again, we're doing this attack. It's the same thing. We've just kind of switched out the filter and switched out the timing, and it's all based on data now rather than on code paths. So this is not real time, but why would you want to do this? Well, maybe you want to read some internal websites that you can't access internally on an intranet, and you'd like to read some pixels from that web page. Firefox currently doesn't consider running SVG filters over foreign pixels a violation of the same origin policy, and I think between Paul Stone's work and ours, that really should change here. CORS or CSP or one of these standards should be applied, and computing over foreign pixels just really should not be allowed. Well, what can you do with this? I'm not going to talk a whole lot about this, but reading pixels is a little bit boring. If you're reading from other origins, you can do things like reconstruct characters on other pages. That lets you read usernames and logins and anything that you can iframe that you can read. So you can't read Facebook, but it doesn't matter. A little bit more subtly, though, we can read pixels from our own origin. So there's an attack called history sniffing, which if you haven't heard of it, the idea is that in history sniffing, you read the link color on a web page. So you as the attacker page make a link to some other page, and you're not supposed to be able to read the link color of that because that would tell you whether or not the user has been there before. But we can just read the link color of our own links using this attack, and then we know whether the user has been there. Okay, so how do I avoid problems with floating point? I've just told you that it's kind of a disaster. There's a lot of timing problems. And the answer is don't use floating point. If you're writing security critical code and the phrase timing side channel has ever occurred to anyone in development, I suggest not using floating point. There's unpredictable results. You have these enormous timing variations. I didn't even show you all of the graphs for that. And it turns out to be extraordinarily processor and build dependent. You also get a fingerprint out of it. If you need non-integer math for some reason, we suggest using fixed point, which entirely coincidentally brings me to the final contribution of our paper, which is libfixedtimefixedpoint, which is a fixed time fixed point math library. It's a C library that implements most math functions that you would care about, add, divide, transcendentals, etc. It's variable width. When you compile the library, you can decide how you want to split up your fractional and integer bits. It's 64-bit, it requires 2 bits for flags. And it's probably constant time. Well, I say probably constant time. We tried really hard. Techniques we used, no data dependent jumps. This means avoiding things like double ampersand. It means using a lot of preprocessor macros. You can't use instructions like div. You get to re-implement division yourself. You can't have lookup tables due to caching and memory accesses. But we can't be 100% sure of the constantness of our code. And this is where I'd really love to talk to Intel some more, because they're totally unwilling to release information about the data dependency timing and honestly the timing in general of many of their instructions. And we can't exhaustively test this. So our library uses things that we think are constant time, and we spent a long time testing, but we can't be sure of it. And really, anytime you write constant time code in this kind of a case, you're battling against every future processor and every future compiler that your users are ever going to use. So here are some brief statistics on libfixedtimefixedpoint. Comparing us to hardware, which is the SSE column, isn't exactly fair because we're a software implementation. And comparing us to MPFR, which is a infinite precision representation in software, is also a little bit unfair because we're fixed precision and we use various approximations. But we feel that if you really need some fixed point math, you need non-integer math, that libfixedtimefixedpoint is worth checking out, and we'd love to talk to people who are interested in using it. So takeaways here. If you're writing security critical code, again, I want to reiterate this, don't use floating point if you can avoid it. There's a lot of pitfalls there, there's a lot of problems, and we all haven't read Goldberg's paper. Writing provably constant time code turned out to be extraordinarily difficult. I recommend reading our paper for some background on some of the things we had to go through. And again, Intel, some help here would be great. And lastly, browsers should really be requiring cores or CSP for computing over foreign data like pixels. At this point, I think that's kind of a foregone conclusion. So future work. That Firefox attack I showed you, it doesn't work anymore. The attack stopped working on version 27, not because of an intentional patch to fix it, but because they switched to the GPU. And at that time, GPUs did not support subnormal floating point. However, NVIDIA engineers have stated that they do now support subnormal floating point, and great for us, there's a slowdown on computing subnormal floating point, but only in some cases, and we have not been able to adapt the attack to that. Additionally, we only looked at floating point. There's obviously tons of integer arithmetic instructions, and we would love to look at what we can break with those because we know that a large number of them are not constant time and are used in real libraries. With that, I'd love to take questions. You can email me there or contact any of the others, and libfixedtimefixedpoint is available on GitHub right now, so go for it.
Questions?
Hello, thanks. This was a great, fascinating talk. Coming from the usability of security viewpoint, one of the last things you said is, okay, we have this libfixedpoint.
Yes.
And it does all these things, but division actually is variable time. So if we are not including that. If you need it, just write yourself. Now, what's the likelihood?
Division is in our library. I meant that we had to re-implement division.
Second?
We had to re-implement division. We couldn't use division instructions.
Oh, you have implemented it.
Oh, we have. I'm sorry.
I completely
what I meant was, if you are writing this, you have to rebuild it.
Yeah, yeah. Okay, great.
So you went in depth on this one attack with pixels, but have you guys explored other places where you might
Yes.
use the side channel?
So we do have another attack. We have an attack on a differentially private database, which I didn't talk about right here today because I didn't want to talk about differential privacy. But we recommend looking at that as well. It's an interesting attack. Unfortunately, there aren't actually a huge number of applications for floating point because there's not that many things that do large amounts of floating point computation. If people have other things that do use floating point math that they've spotted, we recommend looking to see whether this type of attack applies.
All right. Oh, one more question. Yep.
Can you hear me? All right. Ruby Lee from Princeton. I'm sorry to disappoint all of you, but most of hardware performance optimization is based on a fast path and a slow path.
Yes.
If you think about it, there's really no easy way to optimize performance except making the frequent path fast and the infrequent path slow. So there's all over the place in hardware performance optimization, this feature. So the issue is it's extremely easy for hardware vendors to make constant time operations. Mm-hmm. The question is, how much performance are you willing to suffer for this? And so one new line of research that I've been trying to promote is to do hardware optimization through randomization rather than this approach of frequent operation fast and infrequent operation slow. Okay, so if there are randomization security experts in the room, we would very much like to develop this new theory of hardware design that is completely different from before. But if we're going to use randomization for hardware optimization, it must not sacrifice performance. And we think that's entirely doable. So please do contribute.
Do you want to finish that off with a question, or?
No, I wanted to make that comment because I think there's no other way to prevent a side channel or covert channel with any kind of power or performance optimization.
I think that, so there have been a number of processors that I unfortunately cannot remember off the top of my head that have allowed the user to disable certain fast path optimizations and just drop to constant slow path. And I think that for some cases this would be actually pretty valuable. And again, for example, if Intel would just be willing to commit to certain things, saying like, for example, if you multiply a 32 by a 32, it's going to be constant time. That would be really great for a lot of these things.
All right, well, we're out of time, so let's take it offline. Sounds like a fascinating and longer discussion than we have time for. Did you run it in the cloud?
We did not run it in the cloud, but we ran it on a very loaded system.
Well, with that, why don't we thank all of the speakers from the session.